So today what I plan to do is just explore the topics we were doing the previous day, okay? And the next time we will do systematically, we'll go forward into more theory, okay? Today we'll just expand on the various problems that we were looking at the last time, and also the other problems that I had given. So just let me find it for myself quickly. Yeah, the sum of squares thing and so on, right? Okay. Yes, in the end we had come down to this constructing square root of square root of 2. Let me share my screen. I think these are interesting topics, and so as you saw, right, we started with the theory of just irrationals. Means we started with an overview, but through keeping numbers, or rather, yeah, just you can say not really numbers, keeping irrationals at the center, in fact, I would say, right? One second. Students T. Yeah. Keeping irrationals at the center of the discussion, okay, this being a core topic, standard topic. Of course, we spent one class on rationals as well, rather two classes, I would say. But keeping irrationals at the center of the discussion, we were able to touch upon so many interesting things, right? For example, we looked at proofs, or proof by contradiction to be, precise. That kind of argument we sort of tried to pick up. What are the other things that we tried to see through just through irrationals? Even if you talk about, we also looked at construction, right? We will be looking at more of it today, and this will also tie up with our previous knowledge of geometry that we had developed. Okay, constructing the irrationals mean that, so through that we learned. And then also when we tried to ask optimization question on this construction, like how many steps are needed and so on, we saw that that led to this interesting thing about sum of squares, right? Then while exploring more about how irrationals come about, in fact, there are theories that say that theorems that say that in fact all irrationals come from an infinite series and so on, and in fact because the decimal expansion is infinite and so on. But still, um, adding, we looked upon this topic, right? And we will also see more of this today. Adding of infinitely many numbers, many numbers. Okay. Now, obviously, each of these is a topic on its own, right? This goes into hardcore geometry. This goes into proper theory of numbers, means theory of integers, rather, I would say. And this goes into what is calculus analysis, to be precise, right? Analysis. So these new numbers that we invent to serve our purpose of computing the hypotenuse, and also for other purposes, we see that so many new so many, like, some new kinds of branches come in, and some old branches get more texture, right? We get more yeah. So obviously one can keep going deeper into these, but today we will just do try to do more on this side, and analysis, meaning that obviously just estimation and so on, extending what we did earlier. And then we'll also look at a bit more on sum of squares if we have time, and obviously construction. So this will be the first priority. Then we'll look at constructions a bit. If we have time, we'll look at this, and then the next time we will go more into, just we'll come back to irrationals again, deciding when number is irrational, like when a more complicated number is irrational, and some other interesting questions. And from there again we may take inspiration and do some other say non-orthodox topics, whatever, just trying to connect things. Okay, so I think this is the plan. Okay, now let's come to the question of the last time. That was constructing, okay, constructing square root of 2, right? So firstly, it's very important, look, all of you might know the definition of this, but it's very important to understand what this number means. Okay, so let me ask Adityan, what can you say what this number means to you? Any kind of description. Right. So you can see it's very easy to, or rather more convenient to say it like that in a two-step thing. Right. So when you square this number, you get a root 2, and when you square it further again, you get a 2. So fine. Right. Now we want to construct this, right? Now let's break it down, and then we will also try to think. So we'll break it down like this. Number one is that we can construct root 2. Yeah, that is right. We can all construct root 2, right? And what we want to construct is a square root of that. Okay, a square root of a number that we can construct, right? So maybe let me write that in words. This is a way of thinking where apparently you will see that it looks like the problem is being made more difficult, but in fact it becomes easy. And the reason is that we remove the unnecessary conditions. And let's see. Let me write the situation. Let me abstract out the situation that we are having, right? Uh, we are trying to construct square root of a where a can be constructed already. Okay. Now, just I want an affirmation if all of you can relate to this, or if all of you see how this situation is really just this situation. Yeah. This is the situation, right? A is a number which you can construct, which you can are able to construct geometrically. Okay. And then you're trying to construct square root of that number, further square root of that number. So our situation is a special case of this. Is that right? Right? I think I suppose you must have thought about this already, right? This is a special case of this, right? Sort of can consider a square root of something which can construct. Okay. So we will see how we can do this second thing in general. How we can do this thing in general. Is that okay? Then we will be done, right? If you can come up with a way to construct square root of a number that you have already constructed, then you are done. Then you can just construct root 2 and use the same process, right? The benefit is that the same process you can use in if someone gives you square root of 3, square root of 4, you can just use the same thing, or even more complicated thing. A might be some complicated number and its square root you can construct if you can construct a, right? So is this isolation that I'm trying to do making sense, right? Okay. Now let's think about this. How can you construct a square root of a number? So we will try to, let me just leave it there only. That makes sense. Right. Any ideas? Anyone has thought about this? How to make square root of a given a? So given a means that, given a in other words means that you have a line whose length is a. That is given to you. Means that you have already constructed it, right? So it's available to you for use. Yeah, this length is a. Maybe to be more precise, let's mark these. Means that this is available to you. You can have as many copies of this as you want, right? So AB length is a. Right. From here, how can we go about constructing square root of a? Yes, any ideas? No. Okay. So let's do one thing. Let me give you let me give you some configuration, and you try to use that. use that to see if that gives you. What I'll do is I will extend this. Okay, I will extend this line, okay, by a length a. That I can all by a length 1, sorry, that I can always do, right? So this is my c here, and this is my 1 here. Okay, let's do this. Next, what I'm going to do is make a semicircle. So how do you make a semicircle? Rather, we'll make a full circle. So I should have done that first, but yeah. This is a very important construction in any case. I mean, it's used in understanding arithmetic, geometric means, and many things like that. And obviously, geometry itself is just you can make a full circle. Not really needed to make a full circle, but let's see. So this is what it is, right? This is the configuration. AC, okay. AC is the center. Sorry, AC is the diameter. Sorry, AC is the diameter. Right? Now, if you're wondering what is going on or what this suddenly this strange construction, let me put the theorem out that I have in mind first. Then maybe it will be better motivated. So you have this general result, right? You have a line like this, and you have a line like this. Okay, this I had mentioned this the last time. So let's see. And then this is the E, let's say. Okay, so what can we say about the relations between the segments that you get? What can you say about the what is the relation between AE, EB, EC, and DE? What can we say about the relation between these four? Let's. Why I'm bringing it in the middle, because then you can make more sense of the construction even without me mentioning it along the way. That will be maybe more useful. Yeah, what can we say about the relation? Or maybe if you want to put this in more concrete terms, my question would be, if this is 2 and this is, let's say, let me not use decimal, this is fine. Let's just say it's 1.5, and let's say this is 1. Let's say this is 0.8. Yeah, whatever. Then what can we say about these things? Or maybe just use a fraction. 5. Sorry, I mean, this is not, yeah. And what can you say about DE? Find DE, basically, I'm saying. Find DE. So try to use the theorem that's, yeah. Mm-hmm. Is DE 4/5. So can you tell the entire process? AE times EB. Uh, mm-hmm. Yes, right. So that is the key. Yeah, these are equal. Right. So this is the theorem, right? That if two chords are intersecting, then the length of the segments are equal. Okay. So Adityan, do you recall this? Or this is there? This is one of the geometry results which we had done, right? So this is multiplication. Okay. the pieces of the segments, the product will always be equal. Of course, this has to be a circle. Right? These chords have to be in a circle. Yeah, is it okay? Or yeah, so this is the thing that we are looking at. AE times EB is DE times EC. Okay. Maybe you can go back and have a look at it if you want. The proof is not difficult, but it's still a little. Yeah. Anyways, yeah, we will see. And but by the way, we won't need this result because our situation is more special. Okay, and I always advocate for using simplest method to do it. So we will not really use this result, but at least you can see how products and all are coming in, right? And so square roots can also come in naturally. So let us mark the center. Okay, let's say if the center is O hanging over here, right? Center is O here, right? Then my question is, first simple questions is, what is AO? Again, it will not be that very useful maybe, but let's see. What is AO? What is AC? Right. Hmm. Right. That's right. Yeah. Plus one. Okay. Yeah. So that's what AO is. Right. Now, if I draw a line from here, again, so this is the other chord. So my two chords of interest are this vertical one and the horizontal one, which is in fact the diameter. These are the two chords that I'm interested in. Okay. Yeah. Let's mark them. Mark them. B is here, right? B is here. Now, my first question is, okay, my first explain this further is this is perpendicular. Okay. Now, is it intuitively clear to you people that Bx is equal to By? Is this intuitively clear? Just based on symmetry, right? Bx is on that side, By is on this side. This is the diameter. Both sides are same. Okay. Bx is equal to By. I will suggest that you try to prove this later on more rigorously. It is not hard, just some congruence observations you have to make. Okay. But for now, this is true. But please try to prove it more rigorously. Okay. Yeah, because a lot of times symmetry will help you to conclude certain things, but then you have to write the proof. Okay. And here it's easy enough, but sometimes it's so prove this for homework maybe. Yeah. Anyways, for the time I'm removing this. All right. So those two are equal. Okay. Now let's try to find Bx. Let's try to find Bx and see what it is. Shall we? You can use any method you want. You can try to use Pythagoras theorem. You can try to anything comes to mind. So Bx is a Bxy. Xy is our chord and AC is our chord, and they are meeting at the point B. And you have the lens with you. Think about this. It is indeed root A. Okay? It is indeed root A. Again, can you elaborate on this? How you got it? Mm-hmm. Hmm. Hmm. Right. Nice. Okay. Okay. Other than you follow this, nice. This is a very nice way to find bx, isn't it? Right. I mean, and also very interesting way to get square root. Right. From here you get bx equal to square root of a. It's very. I mean, I just this is not my idea. I had definitely seen it at some point, but I like this a lot. Obviously, there are. This actually goes into theory that says that any number that you can construct will be basically a number with several times square root done to it. That says that you cannot construct. It's like you cannot. And how do you prove that is very difficult. I mean, it's a bit difficult to basically explore the space of all possible things you can construct and so on. But that aside, it's just saying that these are like the only things you can actually construct. I mean, not that, but anything you can construct will be of this form. It doesn't even say that everything of this form can be constructed. So it's like anything you can construct will probably look like something like this. But it should have only have square roots and fourth roots and eighth roots and things like that. No third roots and sixth root. Those will never be possible to construct. Okay. It's very fundamental because the distance formula or the distance that you compute from the Pythagoras theorem only gives you a square root. And if you repeat it, you get a fourth root. And if you repeat it again in any complicated way, you can kind of feel that you can never sort of get a cube root, or never you can never get a 99th root. It's impossible, right? Because always you're applying the distance formula or the Pythagoras theorem. And Pythagoras theorem only has square roots. So every time you'll get some sort of a, there might be a lot of roots in the picture, but they will all be just square roots or fourth roots and so on, repetitions of square root. But of course, that's not a rigorous argument, but it's a feeling. A very interesting thing. I mean, this was an open question. The Greeks asked this question thousands of years. I mean, I think 2000, 2,500, right? And it was finally proved after the rules of the game of construction were clearly laid out. You see, right now you would realize that it's not very clear what we want to construct. Is not very, like, you cannot explain this to a computer. We can understand it amongst ourselves, but it's not algorithmic. You can't really write it out. You can feel that, right? I mean, what is exactly the rule and what are the, it's not very clear to write out. So that's reason why you cannot really say what you cannot construct very clearly. But never mind. Coming back to our topic, I mean, that's just a place to explore maybe once you have more maturity in these things. So bx is square root of a and you're done. But I would like to not use this technique at all and just calculate square root of a by just by more simpler tools. What if you did not know about this formula? Okay. And you can already feel that because it's a very special situation. So find bx without using that formula. Let's see. Let's see if we can do that. Right? How can we do that? Maybe as a hint, you can try to use this maybe. So you know the length of OX. See what that is and You can use that. Okay. Yep. What is OX? Right. What is its length? Absolutely. Right. Nice. Right. So you have a Pythagoras situation once again. OBX is a right triangle. If you want, you can draw it separately. The question is, do we also know what is OB? Okay, do we know OB? We should know, right? OB, because we know AB and we know AO. So OB is just the difference, right? OB is just the difference. So OB would be A minus A plus 1 by 2. Right? That's what it is. So what do we get? We get 2A minus 1 by 2, that is A minus 1 by 2. So here the A is bigger than 1. That's the reason why this is happening. Yeah, never mind, that is just a small detail. Yeah. Yes. Now where can we find Bx? Now it's very simple, right? Just apply the formula, okay, and find what Bx is. So OB is clear, right? OB is just the difference. So can we find Bx? OX square. This is just a small calculation. Bx square, and yeah, let's just put the values. This plus, no, it's wrong. Yeah, to change everything. So OX square will be BX square plus OB square, right? And so now you can put the values and so on. So please complete it. Okay, it's very simple. Just complete it. And you will see from here that obviously you'll get the same answer, square root of A. Just complete that part, okay? Put the values into the calculations. Okay. You can also put some numbers and see that you actually get square roots if you want to see it for numbers. All right, so this was just the constructions. It's the way to get square root of a. Now you can do the problem for square root of 2, because you can start with square root of 2 and you can try to complete it. Do the same thing, right? Fine. If that is okay, then let's use the same ideas of, circle, so on, to try to construct another interesting sort of, thing. That would be, yeah, given a, construct 1 by, yeah, we will not complete this problem. We will just see the idea and then we'll leave it there and maybe complete it. Right. Again, you can imagine this can be a useful question, because you can maybe construct some number like 2 plus this, and if someone asks you to construct this, you don't have to again think of a new way. You can just use this process of starting with a and doing 1 by a, okay, of constructing 1 by a. So that's the thing. Even 1 by square root of 2 you can construct using this. Though yeah, 1 by square root of 2 is just simple. It is, we'll see, it's 2 by whatever. Anyways, let's keep moving. So let's think about this. So once again, the thing is that the first number is, we have this available to us. Yeah. How do we construct 1 by a? Sort of an inverse. Okay. Yes. So again, you can keep. So basically, you have to try to think of this, because as I'm intending to do this as a similar thing to the last one, you can just try to just this kind of picture in your mind, right? This kind of picture like this, and one of the pieces is a. Okay? You can keep this picture in mind, and you can keep one of the pieces as a. Maybe you can keep this a. Now the other pieces are sort of free, not all of them, but yeah. How should you make the other pieces so that one of them, so you have to decide two of the pieces so that the third one, or that will rather be the fourth one, becomes 1 over a. You can think it's I mean, at least it should look plausible, because you see, how do these things like 1 over come from? They are all defined in terms of multiplication, right? What is 1 over a? 1 over a is just a number x such that a times x is 1. That x is 1 over a, right? So sort of comes from multiplication. So you think about, maybe you can also write like this: A times BC is equal to A times BC is equal to dB times BE. You can write this because this may again help you to think what should I take as dB or BE so as to improve my chances. So you can think like this 1 by A is sort of fits like this, and you should get a 1. So in particular, what should you take as dB and BE? Maybe you shouldn't even draw the full circle. You just take something like this. What should you take as your these things, BE and dB? This piece dB and the piece BE. So what should you take as dB and BE so that the other thing really pops out? This part turns out to be, after you make a circle, this part should turn out to be 1 by A. And the other is this portion should turn out to be 1 by A. So if you want to do back calculation, you can just imagine that this is 1 over A, in the sense that you can, this is 1 over A. So if this is 1 over A, what's the easiest things to take as dB and BE? What are the most natural? What's the most natural choices for dB and BE? So try to look at this, right? You want your BC to be 1 by A. If you want your BC to be 1 by A, then dB times BE should be 1, right? Just doing a back calculation. So what should I take as my dB and BE? I mean, there would be many choices, but what's the most natural choice? Yes, we can just take both to be 1. Right? That is the most obvious thing to do, right? You just take this to be 1, then this picture fits, right? And now you can just go back and try this. So what do you have to do? Really, what you really have to do is you take that to be, once you have done your backward calculation, this is the case. Now, how would you complete the problem? You just say, okay, I will make a circle with these 3 points. A, E, and D, right? It will be more vertical, less vertical. Yeah, I mean, it's an ellipse. Something, whatever. You get a circle like this. See my point? It's drawing is very bad, but yeah. Okay, if you do this, now when you extend this chord, you pretend that now you extend the chord, right? Then again, by the same formula that we have been looking at, right? AB, I mean, it's all there. We have just, that's what we have done, right? Equals to BE times BD. Use this formula, you get the BC to be, this is 1, BE is 1, BD is 1, it's 1. You get BC to be 1 over. Just comes out. So see what I did? I first took the triangle, right? But obviously, I mean, you can't really construct the 1 by A, right? You can imagine. So the idea is that you imagine that you can construct it, and then you try to imagine what the other two segments should be, given the theorem that you know, right? But then obviously to write it, the circle will not be there in the picture to start with, right? Just be this. Then you make the circle and you take the end point where this thing hits the circle. These are general strategies in construction. You sort of assume that you can construct it and you study its properties, and then you see if you have enough properties to actually make your construction from there. All right, so I think this is fine. Yeah. Any questions with this? There are more interesting ways to construct this. This is a very important construction in what is known as inversive geometry. There, one has to construct this in a more with more conditions, I should say. Yeah. But anyways, is this okay for us? Okay. Okay. How? Yeah, I think so. Yeah. Hmm. Hmm. Okay. Right. Okay. Hmm. Okay. 2AB from right. So the line will be perpendicular to AB, but okay, something like this you're saying. Parallel to AB. So okay. Mark these. Right. Okay. Yes, that looks correct, right? Because as you can see, the DE by AB would be equal to EC by again its magnification would be BC. That's right. Yes. So from here you can figure out. Let's check it. It's 1, and yeah, EC is 1 and BC was A. Interesting. So this is also 1 by. Yeah, this is perfect. Yeah. So and there are other ways using tangents also one can do. Right. This is just okay. I mean, essentially, all of it comes down to right triangles. Is that right? All of this comes because even the construction I did, that's also, I mean, basically, we don't need the full power of the power of point, and we don't need the full power of these distance formulas. I mean, one can basically point is that this is basically a right triangle. If you're making a circle, making a semicircle or whatever circle like this. This is basically a right triangle, and then basically using similarity there as well. So yes, but that's certainly a distinctive session. Okay, right, right. So now let us, with the time that we have, let's move on to the one of the other questions we were doing. Yeah, that is from the series part, where we have to understand if it's finite or not. Okay, let's start with the easiest only. Let's start with the first question. So yeah. So Adityan had sent me some interesting. So what he did, I think, was he calculated, right? Calculated till some extent, and is able to see if that is converging or not, if that is stopping or not, sort of stopping, sort of bounded or not. Yeah, and that technique is good. It works for some, but sometimes it fails. It's so in the last few problems, his answers were not correct, because it seems though as it's they are stopping, but then they are growing so slowly that you know they'll still become big after enough time. Okay, so first of all, let's say for this, right? This going to be finite? The question really is this finite if you keep adding more and more things? Or can you give a number such that these will be less than that number, no matter how many of them you add? That is really the question. Yeah. So yeah, one thing is what Adityan has done through some calculating first few terms and then seeing a pattern. So that is good. We want to see if we can say it more conclusively. Okay, by using the comparison argument and so on. Let's see. So in most of these questions, we're just going to compare it with the geometric series, right? With the series with the series, because this is our this is our pivotal series which we are going to use. Because see, first of all, we know conclusively that this is finite, right? This is always less than one. In fact, we had seen that this. We know that no matter how many times you do this, this will always be less than one. Each of them will be less than one. We had seen this using geometric picture, and so on. Always less than one. So how can we use this series to conclusively say that this one will also be finite? This one will also have an upper bound, a number which all of these are less than. And that should be fairly clear, right? Because as you can see, 1 by 2 square will certainly be less than 1 by 2, right? Okay. And similarly, if you take the next one, then 1 by 2 square is less than 1 by 2, and 1 by 2 to the 4 is less than 1 by 2 square, right? And so to be more clear, so you can understand, 1 by 2 square, 1 by 2 square is less than 1 by 2, right? Is that okay? Because the higher powers you take, the smaller your number becomes. And 1 by 2 to the 4 is less than 1 by 2 square. So you can add them. And you can add them, right? That means that this plus this will be less than this plus this. Okay, is this okay? Clear? Right. So with this, you see, with this you get this, and just continue the same thing. Let's continue the same thing here and here, and so these guys on the left, they are always less than the guys on the right, but the guys on the right are already less than 1. So these are also less than 1. So this is the comparison technique that I was referring to. Okay, this is a very straightforward comparison that we have done. So okay, it's okay. Is it comfortable? This is okay. Adityan, is it okay for you also? Yeah. Okay. Right. So now let's go to the next one. The next one is more interesting, as we have 1 by square root of 2. Then we have 1 by square root of 2 plus 1 by square root of 2 square. Similarly, we have this. Yeah. So again, can anybody cook up an argument? So again, the answer is finite. That uh, you would already have guessed that, maybe, right? If you plug some of these in a calculator, tried it, then you can easily say that this is finite. Should be finite. That's a strong hunch that we have. But how can we conclusively again show that this will be finite? No matter how many of them you're going to add, they still remain less than some number. So this is not going to be as easy, right? Because the numbers, I mean, 1 by square root of 2 is bigger than 1 by 2, right? Because square root of 2 is less than 2, so it's bigger. So then how can we say this for this one? Or is it even easy to just use comparison? So let's try to simplify it first, right? Let's try to just simplify this. Let's write it. It's 2 times square root of 2, right? This is, yeah, even it is 2 times, no, I mean this is just 2, sorry, yeah. And this is 1 by root 2, 1 by 2, 1 by 2 root 2, 1 by 2 square, right? And then similarly, this can help you to think more clearly. So there is 4 here, then there is 5. That's 1 over 2 square, and this is 2 square root 2, and so on. Next step goes on. So is there any interesting observation we can make here? Is it less than 1? Are these things less than 1? Can we say that? Certainly not, right? These are not less than 1. Already at this stage, it is more than 1. Okay? So it's not less than 1, but these are still less than some number. And once again, we want to use that geometric series for comparison. Once again, we want to use that 1 by 2, 1 by 2 square, 1 by 2 cube, and so on. How can we do that in this case? So you see, where we have expanded it, simplified it, as you can see on this side, so that you can see more clearly how, in some sense, there are two copies of the 1 by 2, 1 by 2 square, the geometric series. There are two copies of that in this. Can we spot it? Let's see. Right? So what do I mean by two copies? Look, whenever there is a square root, you can take that term separate. So you can take the terms which have a square root separately. So that's the first idea, right? And you separate the pure terms. You do the same thing here. You take the terms which have square roots separately, and the ones that don't have square roots, you write separately. And you do the same thing here also. Look at the terms which have square root. The first term, the third term, the fifth term. Look at the pattern inside. Right. The terms which have a 1 by that have a square root of 2, you group them, take the square root common, and then you can see another geometric series evolving in the picture. This will evolve as a geometric series. In the next step, you will get 1 by 2, 1 by 2 square. There will be an addition here as 1 by 2 cubed. Right? In the next step to that, there will be an addition inside the square root wala term, inside the square root term. Right? Here you will have an addition. And so on it will go. Right? But then it's very clear, right? Because there is a copy of the geometric series that is evolving here, which you know is less than 1. And there is a copy of the geometric series here, which is less than, this is less than 2, because this will be less than 1 and this is less than 2. But anyways, there is a bound, right? This part will be less than 2, and there is this already, so that's less than this, and anyways, I mean, you can put a bound, right? The idea is to group. So this is, tricky, but if one, basically the point is you group it and you see two different, two geometric series, not different, two copies of the same geometric series. There's two copies of this lying around. So you have to separate. You separate this unrecognizable series into two recognizable series, into two recognizable summations or additions, which are bounded. If two things are bounded, then their sum is also bounded. Something like that. Okay. Yeah, these problems are slightly more mature, so we will not pursue them too much beyond this. This is a good trick, right? Okay. So now, given this idea of comparison, please try the other problems that I have given.